Hello everybody. In the previous video, we saw the impact of zonal EE architecture on ADAS. In this video, we will take, for example, a specific ADAS feature, automated lane keeping assist, as an example, and we will see how zonal EE architecture impacts the integration of this particular feature into the vehicle. Now, we will do this case study integrating automated lane keeping system in zonal EE architecture. We will see first the traditional versus zonal approach. We will see the comparison. In the ECU layout, a distributed architecture is there and dedicated ECU for steering control, separate radar, camera processing. But when it comes to zonal architecture, centralized HPC, this word is very important. Centralized HPC plus zonal controllers handle sensor fusion and actuation. Now, when it comes to wiring complexity, high individual LIN CAN connections to steering, brakes and sensors. So, for every actuator like steering or brake or sensor, there is an individual LIN or communication protocol connector. But when it comes to zonal architecture, this is highly reduced because we are using Ethernet backbone plus smart distribution. And as I already said, Ethernet backbone is powered by TSN, time sensitive networking. Now, coming to sensor integration, hardware to specific ECUs, example camera to vision ECU. Now, plug and play via zonal gateways, example front camera connects to nearest zone. Okay, so here you can plug and play. So you can add like a external entity and it works as an internal entity. Now, coming to VOTA updates, this is VOTA updates in distributed architecture is very limited, but when it comes to zonal architecture, it is seamless. It is not infinite, but it's definitely far more than in distributed architecture. Now, what are the key benefits of zonal for ALKS? Faster sensor fusion, cameras, radars, lidars feed data to the central HPC via zonal hubs, enabling low latency fusion. Okay, so this is critical for lane tracking accuracy because of the physical presence of the central HPC. This feeding the data from cameras and radars and lidars becomes more easy. For example, Tesla's zonal architecture processes 8 cameras through single FSD chip, reducing latency and distributed system. Now you understand. So 8 cameras data is going to one single chip. So naturally the processing velocity or processing speed is very high, thereby increase or reducing the latency. Okay, now when it comes to dynamic actuation control, the steering and brake commands are routed through zone controllers. Example, from left zone manages steering motor, right zone manages braking, or the front left manages infotainment. So depending upon the physical location, the routing is made easier, thereby improving response time. Now, when you scale the vehicle to L3 hands-off mode, okay, it adds redundancy, and adding redundancy is easier in zonal designs by replicating functions across the zones. So, in case you want to replicate the functions across the various zones, this zonal mode is more easy and more conducive. And when it comes to fail operational power, it ensures ALKS stays active even if one zone fails. Now, coming to the technical challenges and solutions. Challenge is latency in steering feedback and zonal architecture solutions. Okay, now challenge is latency in steering feedback, and the solution is it use time sensor networking over the Ethernet to prioritize ALKS control signals. Now, when it comes to safety certification, it isolates critical ALKS functions in hardware partitions. For example, NVIDIA's lockstep GPU cores. And coming to the mixed criticality ALKS plus infotainment sharing HPC, hypervisors, example QNX, and the solution for mixed criticality is using hypervisors, example QNX, AWS IoT FleetWise, and enforce real-time ALKS task scheduling. Okay, so these are the key benefits of zonal for lane keeping system. Now, when it comes to real world implementation, we will see some examples. For example, Tesla uses a hybrid zonal approach with centralized autopilot HPC and zone controllers for actuators. Okay, and automatic lane keeping system benefits from OTA updates to improve lane centering logic. So, lane centering logic can be directly uploaded into the vehicle with the help of OTA. Now, when it comes to Volvo and Polestar, zonal architectures enables pilot assist to evolve from L2 to L3 via software updates, and this is again enabled or facilitated because of the zonal architecture. Now, coming to BMW Neue Klasse, it relies on the zonal controllers plus Qualcomm Snapdragon Ride for LKS, reducing ECU count by 30%. Now, comparison with other ADAS features in zonal architectures. Okay. Now, when it comes to, let's see the ADAS features. First ADAS feature is AEB, automatic emergency braking, and zonal integration advantage is central HPC process radar camera data faster, reducing reaction time. Okay, it reduces the reaction time. This is very important. It reduces the reaction time. And Volvo's zonal AEB uses radar fusion. Okay, this lidar fusion is enabled because of the lesser reaction time. Now, when it comes to parking assist, the ultrasonic sensors connect to the nearest zone controller, reducing wiring. And the Ford zonal architecture simplifies 360-degree camera integration. Okay, and when it comes to traffic jam assist, combines data from multiple zones, which includes cameras from the front cameras, rear radars, and it combines the data seamlessly, or sensor fusion happens seamlessly. The example is the Mercedes zonal setup enables smoother stop and go control. Okay, so this is the example of traffic jam assist used by Mercedes Benz. Now, what are the various challenges to consider? Latency sensitivity for real-time ADAS function, example emergency braking. Okay, now this latency sensitivity is a very important challenge. I am sure by this time you have understood that latency sensitivity is by default a big challenge as far as ADAS is concerned, and also security risks due to centralized computing. Okay, definitely centralized computing has an advantage because it has lesser points of cyber attack, but once it succumbs to an attack, then hacking or attacking the remaining ECU becomes very easy. So there is both advantage and disadvantage. So legacy vehicle integration may require hybrid architectures during transition. Now, future outlook. Now, zonal architectures will enable AI driven ADAS. Example, neural networks for lane prediction by decoupling hardware and software. Okay, Mobileye's IQ runs on zonal HPC. Okay, so this is very important, decoupling hardware and software. This helps to add new versions of software effortlessly. All right, and it also supports the sensor upgrades, swapping 2 megapixel for 8 megapixel without rewiring. And next is enabling V2X integration. Now, traffic light data routed via zonal gateways to ALKS. All right, so this traffic light data routed via zonal gateways to ALKS, it enables faster response time. The transition from domain-based architecture to zonal architecture significantly impacts adaptive cruise control also. Now, let's see how it impacts adaptive cruise control. Now, when it comes to domain-based versus zonal architecture, domain-based architecture in the AC is implemented relying on dedicated ADAS ECU processing radar, camera and data. So, in the traditional approach, there is separate ECU exclusively for ACC. Okay, and therefore it is tightly integrated with powertrain and braking, ECUs via CAN and LIN buses. Okay, adaptive cruise control is very tightly integrated with powertrain, as you can understand, because adaptive cruise control, it very much relies on the modification of the velocity and also the braking operation. Okay, so zonal architecture's modern approach is ACC implementation, and the sensor data is routed to zonal gateways, then to central compute unit. In the zonal architecture, it is routed to zonal gateways, then to central compute unit, and the software defined functions replace hardware dedicated ECUs. Okay, so this software defined functions replace hardware dedicated ECUs. Now, what are the key impacts on the ACC functionality? Okay, how does the zonal architecture affect the ACC functionality to its core? Now, sensor data processing and latency. Okay, when it comes to domain based, dedicated ADAS ECU process radar, lidar, camera data locally and low latency due to direct connections. Now coming to zonal based, sensors connect to zonal gateways which route data to central HPC. Alright, I repeat, understand this sentence carefully. Sensors connect to zonal gateways which route to central HPC far more easily and far more effortlessly. Now, potential latency increase due to data aggregation and routing. Because of the higher data and the routing, there is a slight chance of higher latency. But when it comes to mitigation, that can be mitigated with the help of high-speed Ethernet, which can go up to 10 Gbps and optimized software reduced delays. Alright, and next impact is redundancy and fault tolerance. When it comes to redundancy and fault tolerance, in domain based, if ADAS ECU fails, ACC total fails. This is the biggest disadvantage of domain based. If ADAS ECU fails, adaptive cruise control fails. When it comes to zonal based, centralized compute allows fail operational capabilities and dynamic reallocation of tasks if zone fails. Okay, the centralized compute allows fail operational capabilities and dynamic relocation of task if a zone fails. Now coming to software defined flexibility, domain based, when it comes to domain based, ACC logic is hard coded. Understand this carefully, it is hard coded, it is immovable or it is not flexible at all. Okay, so whenever if you want to change the logic, you need to update right from the scratch. These updates require new flashing altogether. But when it comes to zonal based, with the help of OTA, updates allow dynamic improvements for ACC algorithm. So once, even after the vehicle is bought, and after some time, if the OEM feels like to update a ACC algorithm, it can easily update through OTA, and this OTA is facilitated by zonal based. And similarly, AI and ML integration improves ACC behavior, for example, smoother braking. Okay, so this will also improve the vehicle actuator operation. Now, when it comes to wiring and scalability, in domain based, heavy complex wiring increases cost and weight, and simplified wiring reduces weight and cost. Understand this, here it increases, here it reduces, and it is easier to add sensors for enhanced ACC with with lane change assist. So if at all you want to combine ACC with lane change assist and you want to add some new sensors, zonal based will definitely facilitate far easier update. Now when it comes to power distribution, the domain based ADAS ECU has dedicated power supply, but in the zonal based, power is managed by zonal controllers requiring smart distribution to ensure ACC always has a priority. Okay, as the ACC is one of the most important ADAS functions, to ensure ACC priority, smart power distribution is required, and this also enabled by zonal based. Now coming to the challenges and solutions of the for the ACC in zonal architecture, the challenge is increased latency due to centralized compute. Okay, and the solution is high speed Ethernet and edge processing. Here the challenge is dependency on central HPC. This is a very important challenge, because well, having a central HPC is definitely advantageous, but if this HPC fails, the entire module may fail, the various functionalities may fail. So what is the solution? Redundant compute nodes. So there are some redundant compute nodes which will enable the working of the vehicle even though the central HPC fails. Now complex sensor fusion across the zones, time synchronized networks, example TSN, time sensitive networking. Now when it comes to cyber security risk, hardware security modules, encrypted communication. Now this is something I touched upon in the module about the cyber security and the cyber risk. So the solution to mitigate the cyber security risk is encrypted communication. Now, what are the future enhancements for ACC in zonal architectures? Alright, now first is of course the vehicle to vehicle integration. ACC can leverage cloud-based traffic data for smoother operation. So with the help of the traffic data, whether it is in a particular junction, whether there is a red light or a green light or orange light, depending on that, the vehicle can modify itself or it can adapt itself to the traffic movement. Now, when it comes to predictive adaptive cruise control, AI predicts traffic patterns using centralized compute power. Okay, this is a very how to say promising future enhancement. It predicts the traffic patterns using centralized compute power. And when it comes to collaborative ACC, which is also called platooning, the zonal architecture enables better inter-vehicle communication. Alright, so this is extremely important. So in conclusion, the shift from domain-based architecture, it improves scalability, reducing wiring complexity, and enables software-defined enhancements, ACC enhancement. Okay, so we saw two functionalities and how it is impacting or how it is getting impacted by the zonal architecture, both the lane keeping assist and also the adaptive cruise control. So, but when it comes to adaptive cruise control, it certainly still has some challenges like latency, redundancy, and power management, which are addressed through high-speed networks, centralized compute, and smart power distribution. Now, well, as challenging as they are, definitely in the long run, zonal architectures seem to be more promising, and it is definitely a foregone conclusion that this is certainly an improvement upon domain architecture. Okay, in the long run, zonal architectures enable more advanced, flexible, and upgraded ACC systems, aligning with the trend towards autonomous driving and connected vehicles. So, every automotive scientist and engineer is believing that zonal architecture is enabling movement of the automobile towards L5 total autonomous vehicle. Okay, so hope all of you understood without any doubt the efficacy of the zonal architecture in ADAS. Thank you.